function. Okay. Now the best way to define the wave function is, what is wave function? Wave function is a solution of Schrodinger equation. Is it okay? Now we shall see classical physics and wave mechanics, or quantum mechanics, or so wave mechanics. Let me say wave mechanics. Okay. Let me compare them. In classical physics, what you do, you are going to solve Schrodinger, what you call Newton's. Let me write in one dimension. Later I'll just what you call generalize this one to 3 dimension. Okay. If you have 3 dimension, you will have px square by 2m, py square by 2m, pz square by 2m. Py means I h bar dou by dou y derivative. Is it okay like that? Now I'm getting into first chapter of Griffiths. From today you will have more and more homework. Okay. Yes. F is equal to m into d square x by dt square. Am I right? In case of classical physics, what is the governing rule? Newton's second law. It's a governing rule, isn't it? So in case of quantum mechanics, this Schrodinger equation, it what you call place the governing rule I h bar dou psi by dou t is equal to minus h bar square by 2m into dou square by dou x square of psi plus v of psi. Yes, anyone? In quantum mechanics, this is a governing rule. But remember, what it gives? What it gives? It gives x as a function of t. It gives p as a function of t. Is that okay? But what it gives? It gives some wave function. And it will not give any position or momentum. Okay? It will give, and it will not give anything. Okay? It will give only probabilistic what you call information. It contains only what you call information about probability of the measurement outcome. Nothing else. It will not directly give you anything. Are you getting my point? But if you solve this one, you will directly get position, momentum, kinetic energy. Am I right? T you can write as p square by 2m. Not cap here. I'm not writing cap here. So in quantum mechanics, you are going to define operators. Am I right? Px cap, that's equal to minus I h bar dou by dou x. So similarly, you can define T cap, you can define V cap, you can define H cap, isn't it? But in case of classical physics, those are variable, isn't it? Px, it's a variable. You can find as a function of t. Yeah, it's a variable. Am I right? So T cap as a function, not cap here, classical physics. Okay, T as a function of t, isn't it? V as a function of t. Okay, energy as a function of t, like that, isn't it? But here it becomes operator now. And in classical physics, you can take the same system and you can do repeated measurement to verify all of this. But in case of quantum mechanics, I said wave function gives some probabilistic information. To verify that one, you need to take identically prepared system. Okay, write down that one. To verify probabilistic information given by psi. Okay, we should do the measurement on identically prepared system. Okay, to verify Px, T, V, you can do the measurement on the same system. To verify this what you call solutions and all. Okay, we can do measurement on the same system. Why? Because our disturbance caused by the measurement is negligible. Then only we say it is applicable. Classical physics is applicable. Okay, I'm talking about big object here. I'm talking about small object here. Big object where classical physics is applicable, small object where classical physics is not applicable.
So what do you mean by identically prepared system?
Identically prepared means all are prepared in this one. After measurement, it will not be psi, it will be something else. I'll tell you. We call that one as collapsing of the wave function. Is that okay? You are prepared, isn't it? It contains some information, isn't it? After measurement, you get one of the possible outcome, okay? Again, head or tail, you will get either head or tail. So slit 1 or slit 2, you will get either slit 1 or slit 2. So py1, py2, py3, isn't it? That's what I told in the last class. You will get one of those momentum, okay? But after measurement, look at here. Again, it will take a stand that I am in this state. Electron will take a stand that I am in this state. I am in psi1 state. I am in psi2 state. Isn't it? Your coin will take one of the stand.
Yes.
Either head or tail. Is that okay? So then, after it takes stand, it is not old state. It is a. Yes. Speak out. Any problem?
Sir, same system and both identical system.
Same system. No. Same system says that you are talking about only one. You are counting only one. Better to say identically prepared system. Same system means you are doing the measurement on same system means you are that's a repeated measurement on one system, isn't it? I am not talking about that. Identically prepared system. All systems are prepared in the fresh state. Is that okay? Suppose if our measurement of head and tail, if suppose that was disturbing coin. What is the best example? Suppose your coin is made up of chalk piece material, mud, okay? If you toss the coin, when it falls, it will break. Let me take like that, okay? You made a coin made up of mud. When you toss the coin, when it falls, you will find it will disperse. You will find whether head or tail, but you can't use that one again. Are you getting my point? Then what you have to do? You have to take identically prepared system. Each measurement is killing, isn't it? Each measurement is disturbing the system. Am I right? So thousands of that kind of mud coin. Are you getting my point? I'm saying each of your measurement is disturbing the system. That's why you need to have what you call collection of identically prepared. Now look at here. Each coin which are tossed, they are identically prepared system. Each electron which was shooted, okay, those were identically prepared system. In case of single slit diffraction, each electron was identically prepared system. Is that okay? One electron comes from slit 1, slit 2. When you observe, when you are not observing, it is in the superposition state. Is it clear? Quickly. Now look at here. To verify probability information that is given by wave function, you should take identically prepared system. All are prepared in the same state. We call it in a freshly prepared system. Is that okay? So these are the differences. Keep some spaces, okay? We may add some more here, okay? Keep some spaces out. So again, classically we have continuous energy. Quantum mechanically we will have discrete energy. These kind of ideas will come here, okay? But here we don't talk about position and momentum at all. Is that okay? We don't talk about position as a function of t, or what you call your momentum as a function of t, like that, okay? Again, that information doesn't exist. That indeterminacy will not allow us to have that information actually, but this is the story. Now look at here. Yeah, so quantum mechanics, isn't it? What is wave function? Wave function is a solution of Schrodinger equation, am I right? What does it give, isn't it? What does it give? It gives some probabilistic information, am I right? Look at here, there is one type of Born interpretation here, okay? Again, suppose, look at here, if suppose you have wave function, if you plot mod psi square, we call that as probability amplitude also, am I right? Mod psi square, okay? If you plot mod psi square, you may get some, what you call, like this kind of distribution, isn't it? If you plot mod psi square, you will get this kind of distribution as a function of x at some instant of time. Let me say like that, okay? I have drawn this one at some instant of time. you get some distribution. Suppose let me assume like that, okay? Because I don't know what is V, I don't know what is this, I'm not solving, okay? I'm just assuming mod psi square, let it be like that, okay? Now what does it says? Isn't it? What does mod psi square says? There is one Born interpretation. This is not the only Born interpretation, okay? There are different ways of interpreting that one, okay? I said this contains all probabilistic information, am I right? This is one of the information that wave function gives, that is mod psi square whole square is nothing but probability density. Look at here, this density is the word used in the more general manner. Density need not be always per unit volume, okay? We are talking about one dimension here. This is probability per length. Are you getting my point? Again, you can write it later. This is we call this probability density. I mean, that means density doesn't mean per volume, okay? This is probability per unit length, because we are talking about one dimension, okay? Again, this mod psi square gives probability density, and this mod psi x comma t the whole square into dx, okay? It will give probability of finding the particle. It will give probability of finding what? Position of the particle. Finding position of the particle. You better define this one first, then you can see that this is a density per length multiplied with length per length, okay? Probability of finding the position of the particle in the region x2, in the region, very short region, okay, x to x plus dx. Is that okay? It's a continuous probability distribution actually. We call this as distribution function. We shall solve many problems, then you will understand, okay? This is probability of finding the position of the particle, okay? This is position probability interpretation. There are different Born interpretations, okay? Later, the same wave function will give you energy probability information. The same wave function will give you momentum probability information. Is that okay? Like the different things are there. This is one of that one. Probability of finding the position of the particle in the region x to x plus dx.
So this is a distribution.
So now look at it. If this is probability, then this is probability per length. Dx is not there. That's why we call that means probability per length. So in the most general way, probability density. Yes, tell me.
This is a distribution.
This is called as distribution function. Usually that probability density, that function, we call that one as distribution function. I'll talk about that one later. We are going to discuss probability. But just see this one. Now look at here. Once it is a probability of finding the particle between a short range x to x plus dx, you can integrate this one from a to b. Suppose you have some a here, b here, okay? A here, b here, okay? Suppose if you are integrating this one from a to b, what you will get? You will get probability of finding position of the particle, not finding momentum or something. Later we shall discuss that, okay? Probability of finding position of the particle between a to b, within a to b, okay? We shall see about operators later, okay? I think, one second. Yeah, any question? We shall talk about operator. Some question is there in this. Okay, probability of finding the position of the particle between A to B, between this region. What is the probability of finding the particle? Okay, is that clear? Now look at here. This interpretation also giving some indeterminacy, isn't it? Now look at here. Before measurement, we don't know where is the particle, isn't it? You can only talk about probability of finding the particle.
Sir, I have a question.
Huh.
Sir, this distribution is a particle of the distribution or wave distribution?
Why do you think of that one? Why do you think of again particle or wave? This is probability distribution. This is position probability distribution.
So we are not saying that part.
We are again, our aim is not to prove it is a particle or wave. We are already coming out of that one. Isn't it? Because that we try to explain that one. This is not a wave, remember. This is not a wave like water ripple or electromagnetic wave. It's a distribution. I told you that wave function is quite misleading term. Maybe the whole Schrodinger equation is found by, after de Broglie hypothesis, wave behavior and all. By keeping that it has a wave behavior. But see the use of wave function. It will give only probability information. This is a probability distribution. What is the probability of your measurement? Okay. So to show this probability distribution, you should take millions of identically prepared systems. You should do the measurement. Yes.
Is there no indeterminacy in the probability?
No. Not indeterminacy in the probability. Indeterminacy in the observables, position, momentum, energy, like that. Not in the probability itself. Okay. Yeah, that's quite next level question, isn't it? Now look at here. Now what happened in history is Schrodinger derived one equation like this. Later, after some years, okay, Born gave interpretation for this wave function. Okay, so that's why yes.
But sir, from the solution, can we find the probability to direct find the momentum state?
From psi, you can find momentum. Finding momentum state. You can write this psi in terms of momentum state. We shall see later about momentum state. Okay, we shall see later. Hold on that one. Again, we shall go one by one. I think from this interpretation only we can extend everything else. Okay, we start with this one and we can extend everything. And later we shall show all probabilistic interpretations are similar. In case of third chapter, we are going to merge that one, everything together. Is that okay? Yes. Now look at here. Since this Born interpretation came after this Schrodinger equation, now suppose if you say this is a probability, okay? Suppose if you define like this. Now, what should be the total probability? Suppose in case of coin, probability of getting head plus probability of getting tail. What is this one? It should be equal to 1, am I right? Total probability, again, that should be equal to 1 because probability you usually define as a ratio, isn't it? But this probability is not defined as a ratio. This probability, it is an interpreted one from a wave function. Are you getting my point? This is not defined as a ratio. If you define any probability as a ratio, then your total probability will be obviously 1. Just like number of outcome divided by total number of possible outcome. If you make the summation, you will get 1. That's a classical probability idea. Let me so take it in the next class. Okay. So but here, so this is not defined as some ratio of two things. This is interpreted, isn't it? That's why this doesn't contain the information that total probability equal to 1. That you need to enforce that one. If you integrate this one, suppose if you integrate from minus infinity to plus infinity, that means you are trying to find total probability. Okay, this is a fraction of probability, isn't it? These are the fraction of probabilities. If you want to find total probability, okay, mod psi square dx, what it should be? 1, isn't it? But this information is not there here because this is interpreted. Okay, This information is not inbuilt one here in the differential equation. Differential equation gives some solution. Okay, so suppose if psi is the solution of differential equation, if you multiply by a constant, that's also solution of the same differential equation. So that's why, so this information doesn't exist in this equation or in this interpretation. We need to enforce this one. If you want to do probabilistic interpretation, you should enforce this one. Why? If total probability is not equal to 1, then it is meaningless, isn't it? We call that one as process of normalization. Okay, you need to enforce this condition. After solving this one, okay, you need to find a multiplicative constant to this psi so that this happens. You should make sure that one. We call that one as process of normalization, because this is not defined as a ratio. This is a interpreted one. That's why if you want to, if you want to have any probabilistic interpretation, total probability should be equal to 1. What happens if you are not making total probability equal to 1? Then what happens, look at here, if you integrate from a to b, if suppose this condition is not satisfied, if you integrate a to b, you may get more than 1, value more than 1.
Yes.
If you are not normalizing, you may get value more than 1. Is it okay? You may get any value here. That is quite meaningless. That's why we normalize that one to 1 so that all of these are less than 1.
Less than 1.
Meaningful. Or you can normalize that one to 100, you can talk about percentage here. Okay, that's normalizing to 1, it is for our comfort. Because probability is always less than 1, isn't it? Because we define that one as a ratio.
So basically you want to say that all over the space, the particle, the probability is 1.
I mean, again, particle should be somewhere, am I right?
Yes, all over the space.
Yeah, particle should be somewhere. You should get either head or tail, isn't it?
Yes.
In case of dice, you should get either 1, 2, 3, 4, 5, 6, isn't it? Any of those, isn't it? So when you add all of those probability, you should get 1, isn't it? What does it say? You will get one of the outcome. You'll not end up with nothing, isn't it?
Yes.
Are you getting my point? So that's why total probability should be always equal to 1. So we need to enforce that condition, because differential equation doesn't contain this inbuilt property. Okay, later that solution is interpreted like this. So that's why we need to enforce that condition. We call it as normalization, process of normalization. Okay, we shall see that one later. Okay, in the next topic. First we shall discuss about what is this nature, and again we shall first discuss about classical probabilities. Okay, there are nice problems given in Griffiths which are asked in exams also. So then we shall go for this normalization and all. By then I will give you all integrals, whatever required for normalization. Okay, now look at here. This is,
Sir,
yes.
sir, probability is greater than 1. How I explain it?
No, you can't explain that one. So that's why to make probability less than 1, you should take care that total probability equal to 1. If you enforce the condition that total probability equal to 1, then fractional probability will be less than 1. Are you getting my point? So this is total probability, am I right? This is probability between A to B. This is total probability. Probability of finding the particle from minus infinity to plus infinity, am I right? This is nothing but total probability. If you enforce this condition, this will be less than 1, obviously. If you are not enforcing this condition, if you take some random multiplicative constant to that function after solution of differential equation, you will end up with that trouble. This finite integral may give you value more than 1. Are you getting my point? That's why we need to enforce that condition. We need to find such a multiplicative constant to psi which makes this condition true. Okay? After this one only, you should go for this interpretation actually. Then only this is true. I mean, this is meaningful. Is that okay? We call that as process of normalization, finding a multiplicative constant so that total probability equal to 1. Because you can multiply psi with any constant. That's a solution of same differential equation. You don't have to worry.
Sir,
Yes.
you said that A to B biggest part of psi x squared dx can be greater than 1.
Yes.
How it is possible?
Now, what I'm saying is again, you better read out. Okay, I'll come to this one later. Okay, this is not the concept.
Like
That,
this also.
huh?
I mean, A to B.
Wait, 1 second. Suppose you have taken psi is equal to some e power minus m omega by 2 h bar x square. This is the ground state of your what do you call harmonic oscillator.
Some constant.
No, wait a second. I'll put constant 1. Or I'll put constant 100. Whatever you put, that's a ground state only. We say like that. Is that okay? Now you integrate this one. This need not be equal to 1. Suppose if you integrate from some minus a to plus a, that may be greater than 1. Are you getting my point? You may get into the answer which may be greater than 1 here. Then what I do, I am going to multiply with such a constant. So that is m omega by 2 h bar whole power 1 by 4. Pi h bar, yeah. Pi h bar, no. M omega by pi h bar. M omega by pi h bar whole power 1 by 4. This constant normalizes this one. This constant will make total probability 1. This constant will take care that if you find any finite probability that is less than 1. If total probability 1, definitely fractional probability will be less than 1. Isn't it? If total probability of finding the particle from minus infinity to plus infinity, if that is 1, then probability of finding the particle within some short range, that will be obviously less than 1. Meaningful. Okay? To make it meaningful, you should normalize that one. Yes.
Sir, by normalization, we can say that we are choosing that solution which satisfy our condition.
No. Actually, solution is defined by a function. Okay? We are only changing the multiplicative constant. If multiplicative constant changes, we don't say that's a different solution.
Sir, if you are changing the multiplicative constant, then sir, this is the linear combination of the solution. And if our multiplication constant will be changed, then the solution should also be changed.
No, you are not clear. Look at here. Now, what I'm saying is, I'm not talking about linear combination state right now. Okay, let me take the simplest case, which later anyway you will understand this one. It's not a big deal. Okay. So now, if you change this constant, that is not a different solution at all. Whenever we solve any differential equation, we write suppose y as a function of t is equal to a sine omega x, like that. We write like this, isn't it? A is left to you, isn't it? Again, if a is changed also, that's the solution of same differential equation. Differential equation will not contain any arbitrary constant a, b, c, like that. Are you getting my point? It will not contain that kind of constant. Okay, let me explain that one in differential equation. That's the best idea. How to form differential equation. So that's why this, if you change multiplicative constant, that will not change the solution. Okay, or even if you have linear combination. Okay, psi 1 plus psi 2 plus and so on. Okay, then if you change this multiplicative constant, that will not change the solution. That will not change any of its property, physical property. That's why we are finding such a multiplicative constant which makes total probability 1. Then only our probabilistic interpretation is meaningful, isn't it? If total probability is 3, 4, 5 something, are you getting a point? Then fractional probability will also be sometimes more than 1. That is meaningless. Why I am saying that one? Because so this psi is a solution of differential equation. It may contain arbitrary multiplicative constant. And this interpretation is done later after that differential equation. That's why this information doesn't exist. This probabilistic information is not inbuilt in the differential equation. We need to enforce that condition. We call that one as, what is that? Normalization. Okay, process of normal. I'll come to that one in a moment. Okay. Now we shall quickly see what is this one.
What is the motivation behind normalization, and why are we trying to make it less than 1?
Not less than 1. I mean, total probability. Now look at here. Probability of being head. What is that one? Speak out.
Sir?
What is probability of getting head in case of coin? Head. In case of coin, what is probability of getting head? Quickly. what is probability of getting head when you toss the coin? No, I think, can you hear me? Can you hear me? Probability of getting head and tail. You know head and tail of coin? Yeah. What is probability of getting head of coin? Half, isn't it? What is the probability of getting tail?
1 bit.
Half, isn't it? When you add that one, what you are getting?
Okay, so basically you are trying to say that the probability
What do you mean by total probability equal to 1? Total probability equal to 1 means either you get head or you get tail, isn't it?
Yes, sir.
You should get any one of them, isn't it? When total probability equal to 1, again, look at here. So probability of head is equal to half. So probability of tail is equal to half. How did you found this one? First tell me, how did you found this probability of getting head equal to half, probability of getting tail equal to half? How did you get that one?
Because the possible outcome is 1.
Number of possible outcome is 1 divided by total number of possible outcome 2. I need some other idea. How do you say? Again, suppose if head and tail are not equally priori, I'll do something. I'll do some gimmick so that I'll make it unequal. Then, are you getting my point? Now,
Yes.
so probability is equal to half only when head and tail are equally priori.
Yes, sir. Yes, sir.
Is that okay? Now look at here. What I do is I'm going to say probability of head is equal to probability of tail. It is equally priori, and probability of head is equal to head plus probability of tail. That's equal to 1.
Yes, sir.
Total probability should be equal to 1. What do you mean by that one? You should get either this one or this one. What do you mean by this total probability should be equal to 1? You should get particle somewhere in the x-axis, isn't it? Yes. Now again, from these two, equally priori, total probability equal to 1. From that you get probability of head is equal to probability of tail is equal to half. And this is less than 1 now. That's what I'm saying. If you make total probability 1, this probability between some region that will be less than 1, that is meaningful. Is that clear? What is motivation behind what you call your normalization is, it is not inbuilt one here. It is inbuilt in case of our classical probability definition. I'll argue that one, okay? I'll come to this one. You are not listening one thing, okay? Sometimes I'll explain something because it is needed. Then I'll come to that one later, okay? So because I want to have some more interpretation here. In this class, I want to have some more interpretation, okay? I'll come to this what you call normalization again, okay? So then again, you keep writing your questions, okay? I'll explain that one again. So why we do normalization? Because it is not inbuilt here. It is not inbuilt phenomenon here. Total probability is equal to 1. This is not an inbuilt one in case of Schrodinger equation. Is that okay? Later we interpreted, that's why that we need to enforce. Now look at it. Now, once we say that probability, this wave function gives some probabilistic what you call information, am I right? That's a kind of indeterminacy. Once you say that wave function gives only probabilistic information, or once you say you will get only probabilistic information in quantum mechanics, isn't it? You get only probabilistic information. That itself is a kind of indeterminacy. So we say Born interpretation, what you call, introduces a kind of indeterminacy in quantum mechanics. Just like my superposition state introduces a kind of indeterminacy. Isn't it? I said like that, superposition of state introduces a kind of indeterminacy. You can't say before measurement, isn't it? Now if you say this is the probability distribution, you can't say before measurement what is the position of the particle. Suppose if you want to verify, yeah, I'm saying that this is the curve of probability distribution. How do you verify that one? How do you verify that one? You should take identically prepared system. No, again, what I'm saying is, I said this is the probability distribution. How do you verify? How do you verify this is the probability? I'm saying some nonsense. How do you accept this one? Are you getting my point? I said mod psi square is a probability distribution. It will give you probability of finding something. How do you verify that one? Then you should take identically prepared system. All are prepared in the same state. Are you getting my point? So just assume that graphs are same. Is that okay? So take identically prepared system. All are prepared in the same state. Is that okay? As a function of x. Take identically prepared system. All are in the same state. Not only 3, okay? You should take millions of systems. Do measurement on each. Do measurement on each. So make a histogram. Make a histogram, okay? So some again for more. So this is number of time you found the position. This is the position, okay? So then your distribution will be like this. More number of time you will find the particle here. Less number of time you will find the particle here. This is how you need to verify that one. Quantum mechanical probability distribution, whatever we say wave function gives this information. How do you verify that one? You should take identically prepared system, not only 3. I have drawn 3 graphs. You should take millions of identically prepared system, and you should do the measurement on each, because once one measurement is done, it's collapsed. It is disturbed. You can't do other measurement on that one. Take identically prepared system, do position measurement on each. The result is more number of system gave you the answer here. Less number of system among those millions of system. Less number of system gave the answer here. And your histogram will be exactly same as this one. Are you getting my point? This is how you need to verify this probability distribution. If you take ensemble of identically prepared system. Now you got what is identically prepared system? Which has the same distribution, same mod size square. That is the identically prepared system. Are you getting my point? Then again, once measurement is done, its role is over. Okay. Take an ensemble of identically prepared system and you will get this one. This is the meaning of again, this is how you need to verify probability distribution, and that is true.
How do I prove this is mathematically?
No, this came from solution. This came from solution. Psi came from solution of Schrodinger equation. Psi came from solution of Schrodinger equation. Now I am saying mod psi square is something probability density. That means more probability density here, less probability density here. How do you verify? Suppose I said more probability density here, okay, I'll call it as capital A. I'll say less probability density here, I will call it as capital B. But if you do next measurement, you find particle somewhere at C. Then what do you say? Particle was at C. You are saying something nonsense, isn't it? You can say like that. More probability means your next measurement need not give A. Okay? Probability of being head is half. That doesn't mean next measurement will give you half. Or if next measurement gives tail, that doesn't mean probability of getting head is 0. Are you getting my point? You need to take large number of trials to verify that probability. Any probability stuff. Not only in quantum we need identically prepared system, because each of our measurement is disturbing the system. In classical we can take the same system, we can make infinite number of trials. Okay? In quantum mechanics we can make infinite number of trials. But in case of, again in classical case we can make infinite number of trials. In quantum system we need to take identically prepared system. And again, total number whatever I have taken, there should be millions, of the order of millions. Then you will get very good histogram, continuous kind of curve. Yes, tell me. Yes.
Psi square has some mathematical aspect, or it is calculated from certain mathematical calculation, or it is only concept given by the boss.
Which one? I don't know. What I'm saying is, they did some interpretation, am I right? Later, you do experiment to verify that those interpretation, those things. Schrodinger gave some equation. Why do you believe that one? No, you verify that one. You take its outcome and you verify that one. Born interpreted this is probability. Then you can verify that one, isn't it? By taking identically prepared system. But actually in lab, we don't go for position measurement, okay? Ultimately, our energy probabilities are more and more important in our application of the theory. Okay? Position and momentum are not much important for us. Okay? A probability of getting energy, that is more important for us. We shall see later. Is that okay? But this is the theory that is built like that. Is that okay? Now look at here. You got that point? How we got that one, we don't know. Okay, we need to see their original paper. We don't know how we don't know even how Schrodinger equation we got. I get my point. We don't know that one. How they got that this is a probability like that. Okay, we need to see their original paper, or it might be not there in the original paper also sometimes. Is that okay? Speak out. Yes.
Suppose I have a waveform, side 1, side 2, side 3, then what is the total waveform?
Now, what do you mean by you have psi 1, psi 2, psi 3? You have 3 different states, or you have 3 different particles, or you have a same particle which is in the superposition of those states. Now here I am talking about continuous probability distribution. Later I will talk about discrete probability distribution. You better hold on, okay? You are talking about, I think, psi 1, psi 2, psi 3. It looks like it's a discrete one. Discrete energy states like that, okay? I'll talk about that one. That probability interpretation is quite different. This is continuous probability. Density, you have probability density, probability per length, because you have a continuous curve here, isn't it? Again, I'll try to explain that one in the next class. You need to do some more work on this discrete variable, continuous variable. Okay, then you will understand. There are 2 types of probability here. One is continuous probability density, other one is discrete probability. We don't say density in case of discrete probability. We say probability of getting this one, this one, this one, like that. Discrete one. Probability of getting ground state energy, probability of getting first excited state energy, like that. Discrete probability. But this is position, which is continuous variable. Is it okay? Position is not quantized in quantum mechanics. Position is not quantized. Energy is quantized. Momentum is not quantized. Energy is quantized. Is that okay? When that is not quantized, you have continuous probability distribution. When you have some observable which is quantized, for that you will have discrete probability distribution. Is that okay? So you will get more and more idea when you move on. Okay. So I have written psi 1, psi 2, psi 3, psi p1, psi p2. That's only for comfort. Okay. Only for comfort. Now again you will get much more idea. Now again later we shall see. Okay. This state can be written as linear combination of position eigenstates. Okay. I said this state is a linear combination. Am I right? Superposition of different position states. The whole state psi. Okay. The whole state psi is a superposition of different position states. In that superposition, this position have got more dominance in that superposition. This position have got less dominant. Like that, okay? Later we shall prove that one. We shall try to hold everything into one way, okay? Now look at here. Wait a second. We have one big question here, and you need to read first chapter of Griffiths, okay? Now onwards, okay? So what does this probability distribution say? This probability distribution says, so a particle is more likely to find here, less likely to find here. Am I right? Suppose if you do measurement, you have only one system with you. You have only one system with you. Suppose if you do measurement. Suppose if you found particle at C. Now the question is, our classical thinking always instructs us to ask this question: where was the particle before the measurement? Isn't it? Our classical thinking always pressurizes us to ask the question that where was the particle before? Where was the particle before? What was the position of the particle? Yeah, particle before in the superposition of different position state. Because of superposition of different position state only, this distribution happened actually. Okay, we shall discuss that mathematics later. How this can be written as superposition of different position state. Okay, you have different position states here. But after measurement, you got one of the position state. Am I right? Just like after measurement, you will get either psi 1 or psi 2. Only 2 possibility in case of double slit experiment. But here after measurement, you have many possibility. Among those, you got one of the outcome. Am I right? Yes. Now, where was the particle before? This is just to ask what was the state of the electron before measurement in case of double slit. Similar. But there is a kind of discrete, either slit 1 or slit 2, only two possibilities, head or tail. But here you have many, what you call, position for possibilities. Possible positions are many here, continuous. I get my point. But the idea is similar, isn't it? Where was the particle before? Isn't it? We don't know.
But sir, without measurement, how can we know, sir? After measurement, will produce the result.
Yeah, now you almost in the path.
Sir, can I say
No,
like that?
huh.
I mean, the position of the C,
Hmm.
I mean, the probability of the C, like 1 minus the whole function. I mean,
No.
the probability is 1. If I
No, you can say probability, but after measurement you found particle at C, isn't it? Where was the particle before the measurement? That's my question.
Okay.
Now again, Faisal, can you speak again the same thing, same word?
Sir, if we measure, then the result will, then our measurement will produce the result.
Our measurement only produced the result. How can you talk about before measurement? This is the thinking, that's what I need. You can't talk anything about before the measurement. That is quantum mechanics.
Like a coin which is in the air.
Yeah, when coin is in there,
This is the
whether it's going to be head or tail, you can't say when coin is in air, isn't it?
Yes.
Like that.
That particle is at any position with exact position after the measurement.
After measurement, you will find particle somewhere. After measurement, you will find particle somewhere, definitely, isn't it? It's not like after measurement you will find particle again in case of electron double slit, whether it passed through hole 1 or hole 2, isn't it? Similarly, after measurement you will get one of the position. It need not be C, okay? After measurement you can find particle anywhere, okay? Maybe so in between them, okay? C here. Let me take C here. Is that okay? No, don't go for next level mathematics. I'll explain later. Then you ask the question, okay? If you know quantum mechanics already, ask question according to that situation, okay? Yes, inner product concept. I'll come to that one later, okay? No. So inner product will give us actually probability density and all. We shall see that one later, okay? That's a different
And
aspect.
I think it may be anywhere before measurement.
It may be anywhere. But that's not the answer, isn't it? I was asking where was it is. I mean, you should tell me the position. Where was it before the measurement? Now, again, what I'm saying is before measurement, we can't say anything. That is quantum mechanics. Before measurement, you can't say. Before measurement, it is in the superposition of many position states. Before measurement, you can't say where it was. But at that time, when Born gave this interpretation, there was different scientists take different stands, different school of thinking. Different scientists had different school of thinking. They took their own stand on this one, on this whole quantum mechanics and development. Okay. Yeah. Any questions? Shall I move on? Can you read?
So can we say about the exact position after measurement?
Yeah. After measurement, you can say exact position. I mean, if you do momentum measurement, you will get one of the momentum. If you do position measurement, you will get one of the position. Okay? By doing one measurement, you can't talk about uncertainty. I get your point. I told you, isn't it? One measurement will give you something. I get your point. Whether next fleshly prepared system, whether that gives the same answer or not, that determines, am I right? Next freshly prepared system, whether that gives the same answer or not, that gives the so what you call, whether there is uncertainty or not, isn't it? One system, if you do the measurement, you will get some answer. Whatever the observable you do, you will get some answer. To verify probability, you should take identically prepared system. Okay? That's what I'm saying. Is that okay? Now look at here. Where was the particle before? That was the question. Now there are three stands taken by the scientist. One is the realist position. The realist position. So this is argued by Einstein and his followers, Einstein, John Bell and all, okay, realist position. I mean, John Bell, I think he came later, Einstein and his followers, okay. That means particle was there before, okay. Now the question is, look at here, where was the particle just before measurement, okay? Just before measurement, where was the particle? I'm not talking about where was the particle, so before 1 hour, half an hour like that, okay? Or where was the particle before, so 2 to 3 minutes. Because again, we know in classical physics also, 2 to 3 minutes before it was somewhere else, okay? Where was the particle just before the measurement? That is the question, okay? So now, Einstein and his followers, they argued that particle was there at sea, okay? But quantum mechanical couldn't able to say that particle was at sea. They argued that quantum mechanics is incomplete theory. Particle was at sea, but quantum mechanics saying some nonsense. That's what they argued, Einstein and his followers. We call it as a realist position. Nature will not, play some probability stuff. Nature is not indeterministic. Nature should be deterministic. That's what. So that's what Einstein argued. Then Bohr replied. Again, what I think you might have seen that one. What is that? Einstein said that nature will not play some probability stuff. Nature will not play dice. God doesn't play dice. That's what Einstein said. And Bohr replied that you don't tell what God to do. You don't tell God what to do. Okay, like that. So that is the nature. That's what argued by other people. So that is second one. I'll come to this one. Okay, realist position. There is a history behind that one. Okay. So John Bell. So again, he is a follower of Einstein. He will put some Bell inequality. Okay. Later it is disproved. We shall see that one. Realist position says that particle was at sea, but quantum mechanics couldn't say that it was at sea. It is saying something nonsense. And quantum mechanics is incomplete theory. That's what argued by Einstein. Okay. So second one is the orthodox position. We call this one as Copenhagen interpretation also. Particle was not there anywhere, okay? Before measurement, it is not taking any stand before measurement. Only our act of measurement will make the particle to take one stand actually. Are you getting my point? Our act of measurement produce the result. Particle was not there anywhere, okay? Particle was not having any predefined position before measurement. Are you getting my point? After only our act of measurement, will make the particle to take some stand after measurement. We say measurement not only so he says like that, measurement, observation not only disturb what is to be measured, they produce it. They produce the result. Observation produce some result. Are you getting my point? Observation produce some result. Before that, it was not there anywhere. Or you better say, it was not having any, specified position before that one. Our classical thinking instruct us to ask this question, where was the particle before? Are you getting my point? Where was the particle before? And third one is agnostic position. So again, this orthodox position says quantum mechanics is complete theory, wave function is everything, nature itself is playing some indeterministic things, so superposition of states like that, okay? And we can have only probabilistic information, and psi is the everything. Psi is everything. Nature is playing like that. Nature itself is indeterministic. Okay, and we can only get probabilistic information. Quantum mechanics is incomplete theory because nature is like that. Because nature is like that, quantum mechanics, whatever we are doing, that is correct. That is the orthodox position. Okay, or you can call it as Copenhagen interpretation also, because many scientists argued. Is that okay? Little different way. So together we call that as Copenhagen interpretation. Okay. So third one is the agnostic position. Not that silly. Okay. Agnostic position means refuse to answer. Where was the particle before? Refuse to answer. That's not that silly. Maybe they are not worried about where was the particle before. Are you getting my point? Again, I couldn't get what is this agnostic position actually. Anyone? Whatever he has written. Because we can only talk about, we can only say after the measurement this would happen. Am I right? We are talking about microscopic system where Newton's laws are not valid. I told you, am I right? To verify something, you should do the measurement, then only you can say that this is going to happen, isn't it? Only measurement outcome can say something. Before measurement you can't say, isn't it? Are you getting my point? Before measurement you can't say where was the particle before. Particle is not taking any stand before the measurement. After measurement only particle will show off one of the possible position. After measurement only you will find whether particle passed through slit 1 or slit 2. You will get one of them, isn't it? After measurement you will get to know whether it has momentum py1, py2, py3 in case of single slit diffraction. Is it clear? Quickly. Now look at here. This has some history. They were debating, isn't it? As I told, when Einstein says God doesn't play dice, so Bohr says you don't tell God what to do. Is that okay? That means they are saying nature itself is like that. Quantum mechanics is incomplete theory, because if nature itself plays some indeterministic thing, some probabilistic thing, what we can grab from that one? We can grab only that information, isn't it? From the nature. That's what these guys were arguing. Okay. So what happened is in 1964, John Bell come out with one mathematical theorem called Bell inequality. John Bell was what you call Einstein's follower. Okay. He come out with one mathematical inequality. We call that as famous Bell inequality. That Bell inequality says, okay, if that inequality is true, okay, then quantum mechanics is incomplete theory. They were saying that there should be some hidden variable. The psi is not whole story. There should be some hidden variable in psi. We need to develop that one. So that hidden variable contains the information that, so even before measurement particle was at C. That's what they were arguing. Okay. So John Bell's inequality says, if that inequality is true, then quantum mechanics is incomplete theory.
Repeat again.
Now look at here. Here we are debating, am I right, whether quantum mechanics is complete theory or incomplete theory. So they are saying quantum mechanics is complete theory. It was the whole thing. They were saying quantum mechanics is incomplete theory. It has again we can find that particle was at C before, but quantum mechanics couldn't able to find that one. It is incomplete. There should be hidden variable. They say like that. I mean, there should be hidden variable in the wave function or something which has the information that particle was that at C. Particle was there at C. They say quantum mechanics is incomplete here. Suppose that hidden variable, if you don't know about this, just forget it. Okay. So they say quantum mechanics is incomplete theory. He put one Bell's inequality. Okay. He makes one mathematical what you call derivation, Bell's inequality. If that inequality is true, then quantum mechanics is incomplete theory. If that inequality is not true, then quantum mechanics is complete theory. So he come out with a mathematical inequality, some inequality. It is there in the last chapter of preface. Okay. He will come with one mathematical theorem that he will come with an inequality. If that inequality is true, experimentally true, then quantum mechanics is incomplete. Quantum mechanics is incomplete theory. If that inequality is false, if that inequality is not true, then quantum mechanics is complete theory. He come out with a mathematical theorem like that. Okay. So then what happened is, after some year, that Bell inequality is repeatedly what you call that inequality is not true. It is repeatedly experimentally verified that Bell inequality is not true, saying that quantum mechanics is complete theory. I think he might have come out with that theorem to say quantum mechanics is incomplete theory, because he was a follower of Einstein actually. But that inequality helped us to say that quantum mechanics is complete theory. Bell inequality is disproved. I mean, that inequality will not happen. Bell inequality, disproval of Bell inequality almost proves that quantum mechanics is complete theory. Nature itself is like that. Obviously, if nature is like that, we get the same information, isn't it? So that is the history. So not only that, look at here, lot of experiment happened last 20 to 30 years that you can't even believe that. I mean, now again, you don't question, if you see that kind of experiment, you don't question that whether quantum mechanics is true or not. There may be fault in the formalism, okay? I mean, some basic structure and all. If we could have done in some other way, it would have evolved. While evolving the theory, you may feel like it is not framed very well, okay? But that doesn't mean this whole theory is false. Are you getting my point? While evolving theory, you may feel that, yeah, we have some faulty, just like problem of time or something. That's very, very beyond our topic, okay? So when you see the experiment and verification that we have done in last 20 to 30 years, again, you don't, question that whether quantum mechanics is true or not. Okay, and even Bell inequality, disproval of Bell inequality is one of that experiment, which says that quantum mechanics is complete theory. If that inequality was true experimentally, then we should have gone for some other development. But that is false. It's a mathematical proof. Now we got one mathematical theorem and experimental proof for that one to say quantum mechanics is complete theory. Are you getting a point? Mathematical theorem and experimental proof to say quantum mechanics is complete theory. Maybe in the evolution we may have problem, but it is complete. Yes, and so just read out the question. Now, okay. Continuous measurement will lead to collapse of the waveform. Yeah, again, I just forgot that. Okay, yes. Wait, one second. Just hold on. Just write down. 1 second. Just write down. I have one more thing to say. After measurement, again, now quantum mechanics is complete. After measurement, you found particle at C, isn't it? Now, what is the wave function now? You had wave function like this before measurement, freshly prepared system. After measurement, you found particle at C. Now, so again, what is the wave function now? After measurement, you know that particle at C, isn't it? After measurement, you have very well information that particle at C. Not only that, you have one more information, particle is not there anywhere else, isn't it? Particle at C means particle not there anywhere else. So that's why after measurement, your mod psi square should be like this. It is 0 here, it should be 0 here, it's a kind of spike here. Because after measurement, if you found particle at C, that means you also know that particle is nowhere else. Are you getting my point? That means probability of finding the particle here and here soon after the measurement is 0. And that probability density is high here, very high here. It will become a spike. Is that okay? Now what happens if you do next measurement on the same system? We call this one as collapsing of the wave function. Collapsing to one of the position state. We call this one as position eigenstate. We shall see later. It's a spike. It's a Dirac delta actually. Dirac delta function. If you already know about that one. Okay. The Dirac delta function is position eigenstate. Let me talk about that one later. Okay. It will collapse to one of the position eigenstate. If you talk about what kind of function it is Dirac delta actually. Dirac delta spike. Is that okay? That's one of the position eigenstate So that's the one of the position state that it is superposed of actually. It is a superposition of many position state. That's what I told, isn't it? Now look at here. Now what happens if you do the measurement on the same system? You are not taking identically prepared system. You have done first measurement. On the same system, you are doing second measurement. What would you get? Quickly answer. Guess that one. If you do second measurement, yes. Speak out. Yeah, in principle, you will get same value because probability of finding the particle here it is 0, here it is 0. Then obviously you should find the particle somewhere at C only. Not same, exactly same, because our measurement is hitting with some photon that may disturb, but you will get nearby that one. Are you getting my point? Again, so Dirac delta, area under the curve is 1. We shall see later. After collapsing also, you will get total probability 1 only. I mean, that function, we defined whole mathematics like that only, okay, in quantum mechanics. So what I am saying is, after you find particle at C, you also got to know that particle is nowhere in other positions. That means you first draw this one, probability 0 here. Then try to draw, it will be a kind of spike here. Is that okay? Speak out quickly now. So this is, we call this as collapsing of the wave function to one of the position state. This we call this as position state, definite position state. Can I say like this? This kind of wave function, can I say definite position state? Because it has a very well-defined position. It has not well-defined position, this state. But this has well-defined position.
Sir, this is for only one measurement.
Only one measurement. After measurement, you will get particle somewhere at C only. Because after second measurement, you are doing on this one. Concentrate on this one. On this one, look at here. Your probability is 0 here, probability is 0 here. That's why you should get somewhere nearby C only. But hitting with a photon may change a little bit, but you will get somewhere near only. Not somewhere here like that. Is that okay? Not realistic. Again, look at here. This second measurement should be soon after first measurement. You should not give any much time. If you give some time, if you have any force or something, it might have moved. Okay. Now this is not realistic. Okay. This is a definite state actually. This is a definite state actually. I mean, you already measured. Okay. This is a second measurement. Then you can't say that it is a deterministic theory. You look at this one. This was the first freshly prepared system was this one. Am I right?
Then again, after measurement on the third system.
On the third, you will get C only. C only. If you do any successive measurement on the same, you will get C only because you already know. It's just like you are blocking one of the slit. Then whatever electron reaching the screen should have gone from come from other slit which is open, isn't it? Are you getting my point? In case of double slit experiment, suppose if you block slit 2, then all particles which are reaching the screen are psi 1, isn't it? That means you can prepare a state. One idea. Other one is after measurement, it will collapse to one of the state. Once it collapses to that state, again, if you do successive measurement, it will give the same thing. Once you know that it is passing through slit 1, electron pass through slit 1, then state is psi 1 only, isn't it? Whatever you do. That's what I'm saying. Are you getting my point? It's a kind of collapsing to one of the eigenstate. We say like that, okay? Word eigenstate, you will get to know later. Mathematics you will get to know later, okay? One of the position eigenstate. This is a position eigenstate, Dirac delta. This is a position eigenstate actually.
So can you explain that when that particle is left for some time,
then what will happen if you have any potential? It will evolve, okay? That wave function will evolve with respect to time according to Schrodinger equation. So that's why we say soon after first measurement. What again? Yes.
Sir, but the quantum mechanically energy of the particle is not zero. So, sir, how can we say after some time the probability is not going to change? Sir?
No. Probability, that means what I'm saying is, this is time dependent, okay? We are talking about at one instant of time. This is time dependent quantity. It may evolve with respect to time. It may become some other function. It might have started with this one. After some time, wave function, again, in the most general case, it depends on time, isn't it?
Okay, sir.
Yes.
So it can't be there for more time, sir. So
It will not retain this kind of shape for more time. It will change according to Schrodinger equation and all. Yes, speak out.
But position eigenstate is a stationary state, right? So it will remain there only.
Position eigenstate. No. Position eigenstate. Actually, position eigenstate, you can't prepare a system with position eigenstate, okay? Stationary state means, stationary state is eigenstate of energy only. Stationary state is a word used for eigenstate of energy. Is that okay?
Okay.
Because we shall see that one. How the time evolution happens because of Hamiltonian operator. We shall see that one, okay? According to Schrodinger equation.
Sir, I think for position state we can't say like this term that the stationary state, because the quantum mechanically the energy of the particle is not, so how can we say that the particle
So position state. Yes. To find a time evolution, you have to write any state in terms of eigenstate of Hamiltonian operator. This kind of theorem will come. I'll give that one later. Okay. So, but obviously it will not be like that only. After some time it will evolve. So that's why you should say first measurement, second measurement should be done soon after first measurement, quick measurement, so that you will get a particle somewhere at C only. But you should remember, you have done the measurement on the system where probability is 0 here, 0 here. That's why you should get particle somewhere there only. Are you getting my point? This is a principle.
Sir, when I found a particle at C, then so what about momentum?
Again, simultaneously you can't have momentum information at all. Are you getting my point? Again,
Particle at C, then
you can't say that simultaneously what is its momentum. If that is position eigenstate, you will say that, you will see later. If that is position eigenstate, it is momentum uncertainty is infinity. Because it is definite position state, isn't it? If it has a definite position, momentum uncertainty should be infinity to satisfy uncertainty principle. We shall see that one. We shall see mathematics, okay?
So because the spirit in the position is 0.
Infinite?
Because the spirit in the position is 0, that's why we find the momentum uncertainty infinite.
This width is 0. This width is 0, almost 0. That's why we say it's a definite position state.
Sir, I have studied it lately.
And the expectation value is different, position measurement is different. If you do position measurement, you get something, okay? Expectation value means average of the measurement done, okay? I'll define that expectation value. Measurement outcome, you may get anything, but again, if you take identically prepared system, if you do measurement, if you take average of your measurement, that we call it as expectation value, okay? I'll come to that point. Yeah. This measurement outcome is not called as expectation value, okay? Expectation value is average of the measurement done on the identically prepared system. Okay? That's different. Yes.
Agnostic position.
I too couldn't get that is refused to answer. He's saying this is not as silly as it sounds. After all, what sense can there be in making assertion about status of a particle before measurement? What you do by the answer, isn't it? What you do with the information that you get that you have particle before that one, isn't it? Only thing you can do only after measurement only you can say something, isn't it? So all of this framework are done on the basis of measurement and outcome only. Is that okay? This whole framework, okay? Yeah. So now you can read out. Do discrete probability problems, okay? I'll mention in the assignment. Yes.
In exam perspective, How should I look these kind of theories?
And whatever we have done until today, it will help to understand next mathematics. Just like superposition of position state, superposition of momentum state, it will help us to understand, quickly grab next mathematics. Okay, we are now, from today onwards, whatever we do, that is for exam. I mean, book problem, MCQs like that. Okay, but why I spend this much time? Because you can't grab that mathematics without this much input. Now look at it. If I say I have written one state which is a superposition of momentum state, you don't ask question. It is very easy for me. This is my trick actually. My trick is I'll just build up that one again at least 1 week before, so that when I come to that point, you don't ask more questions.
No,
Okay.
sir, I am asking about general. Is there is only a single way to understand the whole quantum mechanics, the Schrodinger waves or some different ways?
No, you can directly go with the Dirac approach. You can directly go with Heisenberg approach. Because again, Dirac approach which generalizes Heisenberg and Schrodinger approach actually. You can go with Heisenberg approach also. There also you can understand that one. Are you getting my point? So again, that may seems more abstract. That's why Schrodinger approach might have become more famous actually. It became more famous. Okay, but Dirac who generalizes these two approaches. Okay, so I want to give that Dirac's idea. That's why I was discussing like that. Later I can easily connect that one to linear algebra. You can start with linear algebra. Suppose if you take R. Shankar textbook, he starts with linear algebra. Is that okay? He introduces Schrodinger equation later. Like that. There are modern quantum mechanics. They start with different way. Some textbooks start with time evolution as a unitary operator operating on some state like that. Some modern quantum mechanics text like that. Okay, you have different approach to understand quantum mechanics. But we can show everything is equivalent later. Yes.
Sir, is there any way to keep the particle at C again back in same superposition state?
You can't say before measurement. You may find at C. After it is again like this. After you take freshly prepared system, maybe if you take millions of systems, maybe hundreds of them might have found at C, or who knows. I mean that all depends. Okay, but you can't say. You can't say. Once it is freshly prepared, you can't say that it is going to be at C after measurement. You can't say before measurement. Now you compare this one with the double slit experiment, you compare with this single slit diffraction, you compare this with tossing head or tail, you compare and try to understand. Is that okay? That's the best way.